Hello there, students. All right, I hope you've got Project 1A working and didn't find it to be too bad. I mean, I'm sure that there are setbacks along the way and so on, but we're going to be, that's the nature of taking a big project like this. I'll tell you a story, or a joke, or a parable, or whatever the right word is. I learned this from a teacher a long time ago. My teacher said, "Do you know how you eat an elephant?" And I said, "No." And my teacher said, "One bite at a time." Right? Okay, we have a very big project here, and this project is a big elephant, and we're cutting off little delicious bites of him, okay? The only way to eat the elephant is to eat him one bite at a time. Let's take off another bite of the elephant here. It's Project 1B. Alright, now, in Project 1B, what I'm going to have you do is take a very similar idea to what you did before. You're going to be given a latitude and a longitude for a station. Now, we're going to be kind of messing around with Evansville, Indiana, just because that's where I live and that's where I tested it from. But once you get it working, you're going to use the city that I sent you and the latitudes and longitudes of that city and so on. And then you're going to also use the Julian day, and from that information, you're going to compute the solar elevation angle and the solar azimuth angles at any given time of the day, or maybe more accurately, every time of the day. You're going to have a big array with one row and lots of columns. I think it's 1441, because there's 1441 minutes between midnight one day and midnight the next, and we're going to do this in minutes. We'll have the elevation angle and so on of the sun every minute, and from that we're going to be able to compute we're going to use that information of what the solar elevation, the solar azimuth is every minute in order for the rest of the calculations here. Now, on that manageable steps or whatever page that I give you on Blue Line, I actually give you a lot of the code that you need. For example, I actually give you this piece of code here that is for setting up that time array. Time in UTC, the UTC time in hours is going to be an array. It's going to have 1,441 elements in it, going from whatever the time is of midnight at local midnight at some location, but in UTC, like for example for your location, and then it'll go 1,441 times later to midnight on the following day. This is one line, two lines of active code, but it could have been done wrong, and it's not the most educational. It's not. I'm not sure what you're getting out of it, struggling with that part of the code yourself. So I just provide that for you. Similarly, the more I looked at it, the more I realized hour angle is actually a pretty tricky thing to get right and hard to figure out if you're getting it right. So I thought I'd go ahead and give you the code for hour angle. This whole thing here is hour angle. You'll just put this code into your program. I give it to you also on the Blue Line page, the manageable steps page. Your variable names might be slightly different and so on, but this basic idea should work where it finds the local noon, the time at which the sun is highest in the sky, and then it creates this hour angle H that is an array of values for each of the times as to where on the sky over the course of the day we are. You might remember that from whichever was at the elevation and azimuth PowerPoint that we did. I think that was lecture 3. Anyway, again, because that's a hard bug to find, because it's hard to make a graph of hour angle and know what's wrong, or how to print the values of hour angle and know what's wrong. I thought I'd just give you that piece of the code. There's plenty of things to be doing here. So you're going to be writing code that creates these arrays, one row by 1,441 columns, that is describing the elevation, and then another one that makes the azimuth of the azimuth angle of the sun at every time of the day. The question is, how are you going to know if it's working? Well, test it using the values for Evansville on Julian day 180. I give you the latitude, longitude, or feel free to look them up, the latitude and longitudes of Evansville, and then do things like, once your program is run, make a plot of T, UTC, and hours versus your solar elevation. Okay, I did that right here. And I get a little graph that looks like this. Now, it's a little bit strange. You'll notice that for a sizable chunk of the day, the solar elevation is actually negative. That's right, the sun is actually below the horizon, at night. So the sun should be below the horizon. And then you can see how the sun breaks the horizon, crosses 0 degrees, and then it goes up during the day, and then it reaches a peak, and then it goes back down. That looks good. I went ahead and said, okay, well, let's look at that noon sun angle, the time when the sun is highest in the sky. Well, back even in Module 1 of this class, you learned how to compute a noon sun angle. I popped the numbers in for noon sun angle for Evansville, Indiana on day 180. that just happens to be the day I randomly chose. And it works. Good. Okay, that's good. Another thing I checked is, did the times of geometric sunrise and geometric sunset make sense? I'm getting that the sunrise happens at about 11Z, which is 6 o'clock in the morning, Evansville time. And the sunset is happening at about 26Z or 2Z the next day, which, let's see, 2Z the next day is about 9 o'clock at night. This is the middle of the summer, day 180. That could be right. The sunset's really late in this. Okay, those make sense. That seems good. We got a little over, what do we got? About 14 hours of daylight. The sun's up about 14 hours. All that looks good. I could believe that. Okay. I plotted a solar azimuth angle. Now, solar azimuth angle as a function of time is really hard to think about. There's actually much better graphs in like the intro textbook of how to think about a solar azimuth angle, but I couldn't get them to work in Octave. So, alright, just if you can reproduce this graph for Evansville, then just change the latitude, longitude, and time zones and stuff for your station. It'll be fine. If you can reproduce this figure, you'll be fine. But there are certain things you can figure out from this to see if it looks reasonable. For example, I've just put over here again the times that we got from the previous diagram of when sunrise and sunset were. Again, roughly 11Z and roughly 2 hours after 24Z. And just right across there to those azimuth angles. I know they're a little bit cut off on this video. But you can see that the sunrise, the azimuth is happening at about 60 degrees off of north. So if north is this way, 60 degrees is not quite to the east, but a little north of east, which is right. In the summer, the sun should rise north of east. And the sunset is at 300 degrees. 300 degrees, let's see, if 270 is west, 300 is a little bit north of west. That also makes sense. In the summer, the sun should set north of west. So they make sense. I think we have the right angles, the correct angles there. But what if you don't get them? What if you're not getting the right values for the azimuth and the elevation? Well, there's a lot of things I've given you on that Manageable Steps blue line page that will help. For example, I give you what I'm ending up with for the solar declination on day 180. I give you what I get for Evansville for the maximum solar elevation on that day, and I'm giving you what I get for the time of the local noon. I displayed those values and cut and paste them onto the page there, and you can display your values and see if they're the same. If they're not the same, then that's the problem. Okay? So once you have them working, then you'll be able to modify it and make it work for your city, not for Evansville, Indiana. So how bad is this part? Well, again, like last time for part 1A, I just went through and I took my program and I deleted all the comments and I deleted all the white space, because I mean, you can put as much white space as you want. The question is how many of those lines are actually doing anything. And I ended up with 43 working lines. Now, not every one of those lines was really all that. I mean, I think I could have thinned it down even a little bit more. And note, remember, I mean, on Blue Line, I'm giving you several of the whole blocks of the program. I mean, I'm giving you the whole thing of how to compute hour angle. That's like 15 of the lines right there. I'm giving you everything about how to compute the times, for the 24 hours period. That's 2 lines right there. So, I mean, the number of lines you're inventing from scratch here is not that great. If you're writing 200 lines of your program here, something's wrong. Stop. Come and get help, because something's wrong. It's not that big of an assignment. When you're done with it and you have it working, here's your deliverables. What you're going to do is you're going to modify the program so that it works for your station that I've assigned you. You'll have to figure out what the right value, is it working for your station? And then just turn in your program using the turn in command so that I get a copy of it. And then you'll be ready to move on to part 1C. Okay, please let me know if you have any questions. I think this part is a big deal. Make sure you get this part working before you move on to part C.